This is then a picture how we treat this in SDC Verifier. If we have welds, we have these classifications, and these classifications depend on the stress direction locally at the weld. Yeah, so our X direction means parallel to the weld, and the Y direction is perpendicular to that weld. So if I have in this simple example, where we use this standard, so the FEM, we have 4 welds. It works in this way. I have, for all materials, I have a W standard, so non-welded. Then I override that for beam components. We skip that because that if you have beam elements, we skipped it for the moment. For all welds in the weld direction, so that's in the X direction. If this is my weld, that is in that direction. I have a weld class of K1. Perpendicular to the weld, I have, so that is in that direction, I have a classification K3. And then I have weld intersections. What is weld intersections? You can see them over here. If I have welds which cross, I always have a stress which is perpendicular to one of the 2 welds. So for all weld intersections, we override that value in the lowest of these 2 classes, which is of course the K3 then. So in both stresses along the weld or perpendicular to that, they become a K3. For shear, they all have K0. And then in this case, there were certain welds here which were of a certain better quality. So we generated a component where the stresses perpendicular to the weld are not a K3 but a K2. Yeah, and this is the resulting plot you see. So we need, if you check a weld classification, you need to check that for every direction of your weld. For shear, it is either not welded, so that's a W0, or welded, which is then K0. For the stresses along the weld, let's first do this one. Perpendicular to the weld, I have red standard quality, blue is K2, is a better quality, and not welded is orange. And for stresses perpendicular along the weld, I have, if there's no weld, it's W0. I have a pretty good class K1 for all my welds along the weld, but at the crossings, I have a K3 weld. Yeah, because that basically the lower quality of stresses perpendicular to my weld appear at this location where I have here, if I have a stress here in this direction. So if I have a crossing weld, so if I have some weld here and then crossing one weld there, I always, if this is my stress, then it's perpendicular to this weld. If we come here, then if I have this stress is perpendicular to this stress, and if it stresses in that direction, it's perpendicular there. So we take the classification of the worst of the 2. Okay. Besides the weld quality, you can also take into account. Yeah, so this is the welds which are between members. So if I have some kind of a lattice structure, and so for these long members which are not at the end, there is no stress concentration. So these are the fatigue levels I need to set. But if I am at a joint, I also have the effect of stress concentration factors, as you see this one. This, of course, is a very bad idea. In crane worlds, that this welding is in general not accepted. That is what they call a K4. So there is a huge stress concentration here at the tips. And what you see in the Eurocode 3, I picked examples from different standards just to show that they are all in the same way. Depending on how smooth I make this deviation, I get a different classification. So if I don't do anything, then I have a fat class of 40. If I improve it a bit, so I have some kind of a curve here, depending on the radius of my curve, I can go from 50 all the way up till 90. What you need to take into account, though, that these detailed stress concentrations, they are based, because why you have a lower fat class is because at the connection here, I have a huge stress concentration factor. If I use a beam element, I do not take into account this stress concentration. But if I have a plate model, then the stresses here already are much higher. Yeah, so these classifications you do here, you only use these the stress concentration classes you only take into account if you do not calculate the stress concentration. If you do calculate the stress concentration, then the effect of the stress concentration itself is already in your model. Then you should not apply that also to your category, because if you do that, then I get a higher stress and a lower allowable. Yeah, so you pay twice. That's not the intention. Yeah, so if we summarize, we can see stress concentration here. Now it's the 13,001. You see the same effect depending on the stress concentration. I get different classes. If I have something I weld directly on the plate, depending on the smoothness or the size of this thing, I also have different classes. And then between the sections, stresses along the weld. So welds which are in line with my member have a little effect on the fatigue classes, but at sections here, so if I have interval sections, I have lower classes than perpendicular. And also here, depending on the quality, I have different allowable fatigue classes. And you see here also quality taken into account. And remember, the yield value is important, but only if there is no weld. Yeah, lifting appliances, same thing. Stress concentrations you have depending on the category. So K0, if I have one continuous plate, I weld them away from the stress concentration factor and I treat my welds afterwards, then it's a K0. If I just remove, if I only have welds outside of the stress concentration region, I have K1. If I have a weld which is at the stress concentration, but I do some modification to make it better, and I grind these tips, then it's K2. If I don't grind the tips, it's K3. And if I do not pay attention at all, I have a K4. Yeah, so same idea. The problem, of course, with these classifications here for stress concentration is, when is something a K3? When you have some kind of a smoothness, and when it looks more like this. So although with beams, if you have a lattice structure, that is of course much faster if you model that way. you always have discussion on which classification is it. And if you use plates, you don't have that. So if we look here, this is a lattice structure. This can be a classification example. So it's not, the classification as such is easier because a beam only has a stress in the direction of the beam itself. So I do not need to write that for different stress directions, but I have now something, okay. If there's no joint, I have no welds and I have a W0 classification. All the locations here, this K1 is, there's 1 to 2 locations where I made a, sorry, this is a combined member. That is in this case a tube with the rail welded to it. That is K1. And for components where I, for all these connections, I have welding there, that is always a K3. And there is one spot here, which is a K4, because that weld is only on the outside. And so if I look, if it is a tube which you weld, you can only weld it from the outside. So the weld quality inside is not known, and that's considered a K4. Yeah, so again here, it is the weld quality which is important, and the stress direction. So here we have a K1 because this is the weld is in the direction of the beam itself. But besides that, the classification gets somewhat simpler. Yeah. Here's some examples where you show the results based on beam results. So these are this is the utilization factor on the upper right picture. So here you can see that for it looks details, but this is basically a beam member with the shapes on. You can see that the over the height of your beam you have a certain value, and this is typically pictures you can get from there. If you go to more detailed models like plate models, you get fatigue results like this, and you can clearly see all the welds popping up, and you can see that here with stress concentration factors you do expect problems. I also have a couple of pictures where you show cracks found in reality based on the, and then compared to the stress concentration. Be aware that sometimes the stress concentrations can be fairly small, and so you need to be you need to make a detailed model to take this into account. This is the effect of a rat hole, and the advantage of a rat hole is, of course, you do not have welds in different directions joining at the same point, but the location of the at the end of the rat hole is important. So if you really want to avoid that stress concentration there, you need to weld something like this, and that's typically the best possible way to do that. So you have a smoothening here locally and a smoothening here locally, and if you just do this, basically if I have a stress in this direction, then this is a sudden change in stiffness, so that results in a huge stress concentration. Okay, so if fatigue is important for the dynamics, especially, so if you want to calculate these things, you need to take into account the dynamics. How do you do that with a crane, for example? We can directly go into stress variation and do that time based, and that is a lot of work. But in old days, computers were not that powerful, so grain standards came up with a solution, and they used some kind of a classification. And I'd like to show you that, and I also want to discuss that although the approach seems different, in the end it's based on exactly the same theory and the same Polgram minor ruler. The only thing, it is a bit more hidden.